Welcome, everybody. I don't know about you, but I was really inspired by that NYSERDA video, and it just really captured in I thought, a really beautiful way a lot of why we do this. A little bit about me. I started out as an energy auditor and envelope contractor in 2001. So I've done hundreds of energy audits. I've insulated attics, encapsulated crawl spaces. And then in the mid-2010s, I started to see the potential for heat pumps and electrification to get deeper cuts in our carbon emissions. And I gradually made a transition into heat pumps. In doing so, I experienced a pretty steep learning curve. As a weatherization tech, I had installed bath fans, I had tied my insulation blower into electrical panels, but there's so much more that I needed to learn in order to install heat pumps safely and in a code-compliant way. And I began to realize that as we look to scale up electrification, there's a huge need for that knowledge among building analysts, among people who are working in weatherization and building performance who are making that shift into electrification. And about the time of the pandemic, I really reconnected with a lifelong passion for writing. And so I've been writing about these subjects, electrification, and also indoor air quality and refrigerant leakage, preventing refrigerant leaks, things that are really key to getting this electrification piece right. You can find my articles in Green Building Advisor and Fine Home Building Magazine. I'm going to be providing at the end of this presentation links to some articles that take you through some of the specific things that I talk about in this presentation. So today we're going to look at very briefly, what do we mean by beneficial electrification? We're going to go through some electricity basics that are going to be second nature to some folks, but I think it's always good to have a little review and make sure we're all on the same page. One of the big things we're going to be talking about is evaluating the need for electrical service upgrades. This can be a major expense in any electrification project, and I'm going to talk about ways that we can figure out whether it's necessary for a particular measure, whether it's a heat pump or a heat pump water heater or an electrical vehicle charger. We're going to talk about how to get the information we need from heat pump electrical specs. We're going to look at the different options that are out here for heat pump water heaters. There are ones that use 120 or 240 volts. There are ones that can be plugged into shared circuits. There's ones that require dedicated circuits. So we'll look at some of those options. And we'll also touch briefly on some other fuel switching opportunities in the home. I'll mention surge protection and power quality in general, and I'll also be touching on some of the common inspection failures that I've encountered over the course of my work. Now I'm going to just do the mandatory disclaimer for electrical safety. This is not going to be a class on how to be an electrician. Electrical work needs to be done by a qualified person. That's a person with the training and experience to do this safely. And the definition of a qualified person is going to vary by the jurisdiction that you're in. Where I worked in upstate, HVAC techs and weatherization techs could install most of the measures I'm talking about today. There were requirements for permitting and third-party inspections, but there was no requirement that the work necessarily be done by a licensed electrician. In other places, especially downstate and in the larger cities, some of this work can only be done by a licensed master electrician. We need to think about safety practices, using the correct tools, correct personal protective equipment, the job site procedures, things like lockout, tag out, so that we keep everybody safe. And also just situational awareness, knowing what the other people on your job site are doing, making sure that if you're working in a live electrical panel, there's not going to be someone that's going to bump into you. And as we start to transition into mildly flammable refrigerants, there's going to be considerations there about spark protection on the job site. The work needs to comply with codes, the National Electrical Code. New York uses the 2017 edition of that. And we also need to use manufacturer's instructions, which contain a lot of useful information. And any work needs to be done with the permits and inspections that are required by your local jurisdiction. What is beneficial electrification? Well, we're talking about replacing direct fossil fuel use, things like burning natural gas to heat a home, with electricity. And we want to make sure that we're doing this in a way that saves consumers money, reduces CO2 emissions and other types of pollution, increases resilience to disasters, whether we're talking about floods, winter storms, droughts, etc., and improves the health and quality of life of the people we're working for. None of these benefits are guaranteed, and that's why it's so important that we all engage in continuous learning so that we can make sure that we get this right and that we monitor our results in the ways that Courtney talked about to make sure that we really are delivering the benefits that we're promising. Beneficial electrification isn't just about fuel switching. Yes, we are installing heat pumps and heat pump water heaters, but a key part of this is increasing efficiency of buildings. It's also increasing the amount of renewable electricity that we have on the grid and making sure that our infrastructure can handle these increased loads, as well as the presence of these intermittent renewable sources like wind and solar. So that includes transmission upgrades, but also electric storage and improved load management and other things that are done at the grid level to make sure that we have a steady, reliable supply of electricity. In terms of residential fuel switching, which is what we're really going to be focusing on today, heat pumps are a key component of this. They address the largest loads in a typical home. But we also want to think about cooking, clothes drying, although it's not a huge part of the overall electrical energy picture. We need to electrify all these things if we're going to achieve the savings that we can get by shutting off the gas meter and avoiding that monthly metering charge. Electrical vehicles, home vehicle charging is becoming increasingly important, and as energy advisors and people working in homes, we're going to need to be aware of those requirements. And there's also important opportunities with lawn and garden equipment. Some of the gasoline-powered lawn and garden equipment, especially the two-stroke engines like the leaf blowers and the string trimmers, are some of the most polluting things out there. And if we can replace those with battery-powered items, we can actually achieve a lot for air quality in general. The nonprofit Rewiring America estimates there's approximately 1 billion fuel switching opportunities in terms of devices and appliances that can be replaced in the United States. One of the questions that comes up from time to time is, if we're replacing fossil fuel use with electricity, aren't we just replacing fossil fuels in the home with fossil fuels at a power plant somewhere? And the answer is no, that's really not true. This is a graph from the EPA Power Profiler that shows the makeup of grid electricity in upstate New York. Only about a quarter of our energy upstate comes from natural gas. The rest of it comes from nuclear, hydro, and a smaller but increasing fraction of wind and solar. So our electricity is already pretty low carbon. It's becoming more so over time. And so because we have access to this low carbon electricity, we can really achieve deep CO2 savings by electrifying various energy uses in the home. Some of the challenges we've got to deal with, one of the biggest ones is just creating the workforce that can do this. And that's not just installers, that's advisors who can help people navigate this process. It's, the people in the back office who are helping with the loan applications. It's a a team effort, and increasing our literacy on electrical subjects in these areas, I think, is a key part of that workforce development. There's other things that we need to deal with: increasing market acceptance, overcoming customers' concerns of, will this really work in the New York climate? We know that it will. We have thousands of successful projects to show. But we still have to overcome some customer resistance. And that's also why it's really important that we try to make sure that every project is something that will be a home run, that will go out and generate more leads within that person's circle of contacts. And then there's infrastructure that we need to deal with, both at the grid level and at the building level. And I'm going to be talking about some of that building level infrastructure today. So really quickly, we're going to be going through some basics of electricity. Electricity is the flow of electrical power or charge that's used ideally to do work that we want to have it done, whether it's heating and cooling, lighting, mechanical work, or information work. Electricity is a secondary energy source, so the uses that we're talking about are really kind of independent of the way the electricity is generated. It can come from solar or from hydro or from a fossil fuel. It's all used exactly the same in the home, and that's part of what the mandate of our utilities is to provide that seamless electricity when we need it. Electricity can be converted into other forms of energy to do work, and in order for it to flow, the charge needs to be able to follow a closed circuit. There are two main types of circuits that we can talk about. Direct current circuits are what we have with most battery-powered devices. We have a positive terminal and a negative terminal. Charge flows one way through our load and back to the other terminal. But the electricity that we have through the grid is an alternating current. The direction of the current flow is changing in our grid 60 times per second. And this is all the electricity that we're going to be talking about today is alternating current. We do see a little bit of DC current in some of these heat pumps that we install, mainly as a communication and signal voltage. So DC provides a constant voltage. If you put your voltmeter on a battery, you'll see that that voltage remains constant over time. The AC voltage that we get from a plug, a receptacle in our house, is fluctuating on this 60 hertz cycle. It's a particular leg of power is alternating between positive and negative, positive and negative. The electricity is flowing back and forth. Our meters, when we go to measure this, need to be told that we're measuring AC electricity. And what it does is it calculates the average using a mathematical formula that takes into account basically squares each voltage over time and averages those, and that gives us our voltage. The voltages change as we move around the grid. At the power plant, we have things in the range of anywhere from 2,300 to 30,000 volts. That gets stepped up when we go to the large transmission lines. It's stepped up because if we go to higher voltages, we can transmit more power with smaller currents, and that reduces line losses. As we get into our local distribution networks, that step down. And then when we get into the homes, it stepped down even further to the 120 and 240 volt currents that we see in the home. One thing I will just mention briefly, you will see the terms 110 volt, 115 volt, 120 volt electricity. Those are all functionally the same. Over time, our grid has gradually and slightly increased the transmission voltages to the homes, the voltages that are coming into the homes because of the increased loads. And the same thing with 220, 230, 230 volt electricity. Those are all functionally the same. So just know that to avoid any confusion. So now we're coming from these distribution lines to the home. There's a device called a transformer that steps that voltage down, and it does another thing. It splits that incoming voltage into two legs that alternate from each other. So we've got the leg that's shown in blue here and the one that's shown in green. Those are 180 degrees opposite each other. So whenever one is high, the other one is low. There's also a neutral tap that has 0 volts relative to ground. And so with these two legs of power and our neutral, we can either get 120 volt current if we go from either one of these legs to neutral, or we can get 240 volts if we have a circuit that goes from one leg of power to the other. What this translates into in our breaker panel is that if we have a single pole breaker, these are the smaller single breakers that you'll see in the panel, that connects one of these incoming legs of power, shown in this, this yellow bus bar, connects that one leg of power through our loads, in this case a receptacle, and back to the neutral bar. Now these two hot bars are, the terminals are alternating. So if I move this down one spot, I'd now be connecting to the A leg of power instead of to the B. There's also grounding in every system that essentially provides a low resistance path in case there's any kind of short circuit or something that will allow the current to flow safely to ground and rapidly trip that breaker, so that there's, reduces the chance of electrical shocks. With these circuits, we can have either shared circuits, ones in which we have multiple things plugged in. That's a typical, residential plug circuit would be a shared circuit. And we can also have dedicated circuits when we've got a appliance with a larger draw, like a sump pump or a whole house dehumidifier. The manufacturers are going to specify a dedicated circuit. That's one that is designed to only have one outlet for that device. When we have a double pole breaker, now this is a breaker that covers two spaces. It connects one leg of power to the other, and between those we have 240 volts. And this is what we're going to have for things like heat pumps, heat pump water heaters, electric dryers, things that are heavier duty loads. We also are going to use these double pole breakers if we're going to install a sub panel. Yeah, Jamie.
Hey, John.
Yeah.
Sorry if you're taking questions at the end.
No, go ahead.
When it comes to grounding, I've had electricians I've sent out, and they need to charge for putting spikes in the ground outside to ground the system.
Yeah.
If they're not already there, how's it grounded typically? Like, just hope for the best, or usually water line. Water line? Yep. Yeah.
Yeah, there should be, there needs to be a central ground in the system, and I think by code now it has to be a rod that's driven deep into the ground. Yeah.
When we talk about balancing the legs, is that just balancing the A and B leg for the box, or isn't that such a thing?
Yeah, that's a good question. So, each of these hot conductors has a rating. If this is a 100 amp panel, each of these live conductors is rated for 100 amps. And if we put all our loads on, connected to one part of to one leg of power, we're going to have more flowing through one leg than the other. And also, those loads won't cancel each other out through that neutral. So that's something to be aware of. It's something that honestly I've just not run into a lot. But in general, you want to make sure that your single pole loads are evenly distributed across the two legs. Amperage is the strength of the electrical current. It's how many electrons are flowing through that conductor at any moment in time. And it can be measured with a clamp-on ammeter like I've shown here. When we do circuit monitoring in homes, for example, with a Emporia monitor or something like that, we're using similar clamp-on devices that clamp around our conductors, sense the fluctuating magnetic fields, and translate that into a measurement of current. Resistance is a measure of how much a particular component or how much an entire circuit resists or opposes flow of electricity. We can harness that to create heat, as in any kind of electric resistance heater, whether it's a toaster or a electric water heater. But in our conductors that are going from our panel to our loads, we want that resistance to be as low as possible, or within at least acceptable bounds. Which leads us to the idea of ampacity. Every conductor has a maximum safe current that it can conduct without overheating. And that depends on the size of the wire. The lower the gauge, the thicker the wire, and the more amps it can conduct safely. But it also depends on the temperature rating of the particular conductor. Some things like non-metallic wire have only a 60 degree Celsius temperature rating. Others might have a 75 or 90 degree temperature rating. And so you need to know that when you are looking at the charts to figure out which conductor you need for a particular application. Circuit breakers are paired with our conductors, and what they'll do is they'll trip if that safe current is exceeded. And that can happen in two main conditions. One are short circuits. That would be an example of, I'm not paying attention to what I'm doing. I put a screw through a wire, and suddenly I've connected my hot conductor to my neutral. A massive amount of current can flow, and if that continued to flow, it could start a fire, but the breaker immediately trips and shuts that down. Breakers will also shut down in the case of overload, meaning more of a continuous overdraw. So if you were to plug in, well, an example of when I've done this is when I had my coffee maker, my toaster, and my microwave all plugged into the same circuit. That was a 20 amp circuit drawing probably 30 amps of power through that. The breaker trips to prevent overheating. It's also important to know that HVAC equipment has additional overload protection built into the equipment to protect both the equipment and the conductors. Power is the rate at which work, whether it's thermal work, heating, or mechanical work, that's the rate at which it's done in an electrical circuit. And it's calculated as volts times amps. So if I have this space heater here, it's plugged into a 120 volt outlet, it's drawing 12 amps. My power is 120 volts times 12 amps, or 1440 watts. There's a little nuance that I just want to mention here because it's going to come into play in our calculations. There are resistive loads, electric resistance essentially. And in those, our current and our voltage are always fluctuating in perfect sync. And in those, our watts will always be exactly our volts times our amps. When we've got an inductive load, essentially a induction motor, these are designed so that the current flow and the voltage are slightly out of phase. And in those, the power will be slightly less times the volts times the amps. And that's called apparent power. In practice, these are so similar that for the calculations that we're going to be doing, we're going to treat them the same. So we can use either watts or volt amperes in our panel sizing calculation. If you want to drill into that further, it's pretty interesting stuff, and it'll help you understand better how electric motors work. But for our purposes today, we can add up our loads either in watts or in volt amperes. Yes?
The question Jamie asked, I didn't hear the whole thing, is it required if we upgrade the panel box to actually run a spike for ground, or can we utilize the old
I'm sorry.
installing an upgraded panel box, do we have to, by code, run a new spike, a ground spike, or can we use existing grounds?
That, I think, I don't know the answer to that, honestly.
Depends on your local site. But you are allowed to use the existing as long as it meets the new code. But typically it doesn't, so you're typically able to put in
That night, I used two different electricians as a sub out,
Yeah.
and one guy does it every time, the other guy never does it.
Yeah, this is one of the things. The electrical code is really long and really complex, and I think there are clear answers, but there's also a certain amount of interpretation that happens. And so, that's one of those things that I think it needs to be done right and safely, and the questions may come down to what your local authority is going to make you do. And so we can use power to calculate energy, and this is what we do when we do various types of energy modeling. If we know the power that's being drawn and how long it's being drawn, we can calculate the total energy being used in watt hours, which is then converted to kilowatt hours, which then is what ends up on our residential electric bill. Kilowatt hours are a metric unit of electricity or of energy, and BTUs are a British thermal unit, imperial measure of energy. When we're talking about heat, these things can be treated as equivalents. We just have to multiply every kilowatt hour that's converted into heat gives you 3,400 and change BTUs. And so if we have a standard electric baseboard is typically 250 watts per linear foot. We have a 4-foot long baseboard. That's going to be 1,000 watts or 1 kilowatt. And we can calculate that that'll deliver 3,413 BTUs per hour. Okay, so that's it for the basics. I'm just going to quick glance at my time. Now we can start thinking about electric service upgrades. And as we electrify homes, start adding loads, we may find that the loads that we're adding exceed the rating of our electric service. And so that may require us to upgrade these service conductors. The utility may want to change out the meter. A lot of utilities are in the process of installing smart meters. And we will probably also need to upgrade the main service panel to accommodate those extra loads. I drew kind of a very typical situation here where the main service panel is inside the home. Sometimes they're on the exterior of the home. Sometimes they're on a separate pedestal. That's very common in rural areas, manufactured homes, and so forth. In which case, if you have a main panel on a pedestal, you'll have a sub panel inside the home. These will typically have service ratings in our area of either 100, 150, or 200 amps. And if we start adding loads to those, we need to know, can we safely add these loads without exceeding the rating of the service? But we also want to have some caution in doing this, because upgrading the service can invoke real costs for the customer. I said $2,500 plus here. I think that's on the extreme low end for a service upgrade. And usually it can be more. If you're talking about a underground service that's a good distance from the road, you could be talking about $5,000, $10,000, sometimes even more. And if you have an underground service in an area where it goes under a sidewalk or something like that, it can add additional costs and complications. But the other piece that's important for this is that service upgrades can cause delays as you need to line up now an electrician and obtain the permits. And we know that most of our heating and hot water replacements happen under emergency circumstances. And so, we have this, usually 24 to 48 hour window in which a customer calls and says they have no hot water. If we can offer them an electric option, we've started to electrify the house. If we can't, they could be tied to that fossil fuel for another 15 or 20 years. And, given our goal to achieve huge strides in electrification by 2050, that represents a real missed opportunity. So getting comfortable with figuring out whether a service upgrade is really needed in a particular situation or not can actually help us to capture more of these emergency change-out opportunities. The code allows for two approaches to determining whether electric service upgrade is needed. Most of the time, we're going to be using the one that's described in NEC 220.83. It's a clipboard method, involves data collection on site, and then a quick run through a spreadsheet. And it tends to be maybe slightly more conservative in that it's more likely to trigger a panel upgrade. But I'll show a case study that shows that these two generally deliver pretty comparable results. The other one is under NEC 220.87, determining existing loads. And this requires energy monitoring data. This was used a lot more commonly in commercial settings where people already had devices in place that could measure peak demand. But now that we have devices like Emporia monitors that we can monitor people's real-time electric use, this can give us the data that we need, and with a really quick calculation can tell us, okay, this house has plenty of extra panel capacity or not. In theory, this should also be very easy to calculate if we can get access to smart meter data. I have never succeeded in getting any of this from my utility, so I've ended up relying on home energy monitors that I've put in on my own.
John, quick question. So
Yeah.
You haven't had to see getting that from the utility for its customer, or do you think even the customer has the data that they need from their smart meter?
Yeah, so I tried to do this for my own house, and you end up emailing this generic link on the website, and you never hear back. And same thing with the phone calls. So if anyone has had success in doing that, I'd really love to hear about it.
The information that they're giving us from the smart meter we do get isn't adequate enough to actually do anything.
At this point in time, that's been my experience. It's a smart meter, so it is monitoring, your use in very small time increments, but you're still only seeing your monthly kilowatt hours on your bill. Hal?
I think a good time to mention is something that's up and coming. There's a pilot project down now where expand
Yes.
And so a span panel is a load shedding panel.
Yep.
The concept is to be able to use some 100 amp services without switching service, but and the panel is actually rated at 200 amps where it'll shed loads. You can take that panel, 100 amp panel, or 200 amp panel, depending on the service rating in the house.
Yeah, I'm going to mention those really briefly later on, but yeah, there's definitely some workarounds if these calculations show that you're over the limit. So this is what, as an advisor, as the first person in the customer's home, this is the data that you'll need to do that 220.83 calculation. The square footage of the home, that's the conditioned square footage. Electrical panel photos, and I'll show you in the next slide exactly what we're going to need to find from those. We need to know the number of small appliance and laundry branch circuits. These are typically 20 amp ground fault circuits like you'd have on your kitchen countertop and in your laundry room. The one thing that you're probably not doing as a standard energy audit that you'll need to add is a survey of the fixed appliances. So this includes things like refrigerators, chest freezers, but also well pumps, sump pumps, whole home dehumidifiers, because those wattages come into play here. We need to know about the existing HVAC equipment, if it's going to stay. And then we need to know the characteristics of the new HVAC equipment that we're going to be adding.
Where does the existing service drop come into play into that checklist?
So this is what I count under the electrical panel photos.
Does a 100 amp panel automatically denote that it can't be upgraded to 200 amp without a service drop change?
I would say that's not universal, but I mean, sometimes we have 200 amp conductors coming into a 100 amp panel. Yeah, so that's something to be aware of. I really think that call is one that I'm always going to want to defer to an electrician in that case. But yeah, no, there are different possibilities.
One, isn't it? To know that the service coming in is going to be able to handle the upgrade?
Yes, no, I mean, I think if you've got a 100 amp panel, this is really where this usually comes into play, is when you've got an existing 100 amp panel and you're wondering, can I make this work with the existing 100 amps? If you can't, then you're bringing in an electrician, and they may say, okay, you're going to have to upgrade the service drop and the panel. In some cases, I think these are going to be kind of the exception. You may be able to replace just the panel, and that'll be significantly cheaper. So, yeah. So that's, but that's generally not a call as a non-electrician I'm going to make at that point. I know in the audience there's several energy advisors that I've worked with closely, and one of the things I'm always asking for is, do you have any better photos of the electric panel? And these are often in dark, hard to reach places. Having really good pictures of the panel is going to make your life a lot easier. This happens to be a really good one that I can enlarge to see the size of the main breaker, that I can read the the make and model of the panel, the number of allowable circuits, and so forth. The branch circuit labels on an older panel, this is usually a mess. And you can use it in a general way to have some idea what's going on. And then you can actually see what's in there. Okay, I've got a 30 amp breaker that goes with my aux heat for my heat pump. I've got another 30 amp breaker that goes with my water heater. So having good, well lit, high res panel pictures is going to be really helpful. We want to take a look at the panel condition. Is there rust? Are there scorch marks where there might have been some kind of damage? Are there loose breakers? Is stuff missing? I mean, we go into houses, right, where the panel cover is missing, and it's kind of terrifying because there might be kids playing in that basement. But also things like the connectors that prevent the wires coming into the panel from shorting out, and missing filler plates. So oftentimes people will pull out a circuit breaker and leave that opening empty so that it's a person could potentially reach in and touch the live conductors. This one has filler plates, which is good, but that's another thing to look at. And just being aware of potential rodent damage, things like that can happen in a panel. We also want to have our heads up for outdated and recalled panels. A lot of these things were installed, in the 60s and 70s, and have been recalled for one reason or another. Is anyone still running into these 60 amp fuse panels? Yeah, we see those. These are absolutely going to need to be upgraded. It's time, and they're typically 60 amps, so they don't have enough capacity anyway, and no way to safely add additional load. So that's pretty much an automatic upgrade. But there are other brands that have been recalled. Pushmatic is one, Federal Pacific, Stablock is another. And there are also these split bus panels that you'll run into occasionally. You'll be able to recognize the split bus panel, and I apologize I don't have a picture, because all the double pole circuits will be clustered together in one part of the panel, and then there's going to be a gap, and then you've got all your single pole circuits. Those, I think, don't necessarily need to be automatically upgraded, but you should be aware that they're not considered great to have because there's no main breaker to shut them off, and so they're they don't have that important safety feature.
In not having availability for new breakers, so if you're adding heat pumps of any sort, you can't get hands on breakers.
Exactly. So that's another consideration. If this, if you run into any of these brands, yeah, you might not be able to find what you need. So just to give you a quick overview of kind of the big view of this calculation, it's broken into two parts. One is the general and appliance loads. And what this calculation recognizes is that no one uses all the electrical appliances in their house at the same time. Refrigerators cycle on and off. Ranges are used, half hour here and there. Lights are turned on and off. So we don't need to add up every single load at 100%. What this calculation does is, you add up, and I'll go over the details in the next slide, but you add up the first 8,000 VA and count those at 100%. And then general and appliance loads that are over 8,000 VA get derated to 40%. And that's to recognize the fact that not all these are going to be used at the same time. Now with HVAC loads, we need to figure out, first of all, what is the total heating load? And that's going to include, in the case of a heat pump, your heat pump and your resistance heat if you have it, plus any additional resistance heaters that you have around the house. And then you need to do the same thing in cooling. So you're looking at, in the case of a heat pump, it's cooling energy use. And you want to figure out which is going to be larger, summer or winter. You don't have to add those together because they're not going to be used at the same time. You need to figure out which one is larger and plug that into your calculation. And once you figure out the total adjusted volt amperes for your general appliance loads, plus the larger of your heating or cooling loads. You take the total volt amperes, divide it by 240 volts, and that gives you your required service rating. So what I'm going to walk you through is step by step how you go through this spreadsheet. It's about 4 slides of spreadsheet stuff, just to show you how quick these calculations can be if you have the right data. So this is for my own house. We need to put in 3 VA per square foot of conditioned space. And that's to account for lights, plug loads, things like that. So I need to know the square footage of the conditioned space times 3. Small appliance branch circuits, these are my 20 amp countertop circuits. I've got 2 of those. The calculation requires you to put in a minimum of 2. And then your laundry branch circuits. This is, again, a 20 amp single pole circuit that powers your washing machine. And if you have a gas dryer, it can also plug into that. So that's our general load. In my case, 8340 VA. And now we get into the fixed appliance tally. So we're not counting stuff that's plugged into our countertop circuits because we've already counted that. We're talking about fixed appliances. So this includes things like bath fans, electric cooktop, electric dryer, in my case, a heat pump water heater, dehumidifier. I realized on this I cut off the refrigerator, but that should also be in there. And now we add up our general loads based on our square footage and our small appliance branch circuits and our fixed appliance loads. And of this 22,000 VA, we take the first 8,000 at 100%. And then anything above that, we only count at 40%. So even though when we add all this stuff up, it comes to 22,000, after the adjustment, it's only at 13,006. So one of the take-homes of this is that while it's really important to count up all these appliances, they don't count as much towards your total as HVAC loads. Now, when we go to think about adding a heat pump to this system, we need to know what to put in for that. And so here, usually I'm doing this at the design stage. So I'm looking at a submittal. I'm not looking at the nameplate on the unit. By that point, it's a little bit late in the game. And you'll see multiple electrical ratings for this. The MOP and the MCA we'll talk about a little bit later. Those affect the breaker and the conductor size that you use. But for this calculation, what we really want to look at are our rated amps. This is what factors into this calculation. Now, in the case of this system, it's 14.81 amps in both heating and cooling. You may get some systems that have different ratings in heating and cooling mode. And again, you're going to be choosing the larger of those two. So to take those rated load amps and convert them into VA, we just take that from the submittal, multiply it by our voltage, and we get our volt amperes. If we want to put in a resistance heater, in this case I'm not, but if we do, its wattage, its VA for these calculations is just going to be equal to its watts. So, our resistance heat kits for our heat pumps are typically rated at 3, 5, 8, 10 kilowatts. That just translates directly into VA. Now, we're down in the HVAC section of this worksheet. And I didn't have any electric baseboard. The furnace that was there is going away, so I don't have to count it in this spreadsheet. I've got my heat pump. I'm not putting in a resistance heat kit. If I did, I'd have to put it in at whatever its rated value is. And this gives us the total amount of HVAC loads that I'm going to be adding to this system. If we had a straight air conditioner and electric baseboard, for example, we might have different numbers for heating and cooling, and we just have to pick the larger of those two. And so we add our adjusted fixed appliance load, our HVAC load, and we get a total. We then divide that by our total service amps. And in this case, the number I'm getting here is 74 amps needed for this system. I have a 100 amp panel, so I'm good. And I actually have some room, if I wanted to add an electric vehicle charger, which is something I want to do in the future. Jamie.
Yeah, this popped in my head, so I'm sorry if it's a little off topic, but have you ever compared the rated amps on the metal sheets to the kilowatt data on the leaf sheets in terms of accuracy between the two? I mean, are they even in line with each other? Is that something you looked at?
So the NEEP data versus the submittals, I haven't. I think the NEEP, we have some folks from NEEP here who might know about that, but I believe that NEEP takes its data directly from AHRI. And so I suspect that those are going to be pretty similar. I also have done some, amp clamp monitoring, and I do find that I rarely hit the max numbers that are shown here, and that would only be in the system cranked to max in cold weather when you're up at your maximum frequency.
Thank you.
Sure.
Is that what that load takes into account, the maximum potential draw at X time?
Yeah, so it comes from the manufacturer, and it would represent, kind of the peak continuous draw. Yeah, it doesn't represent, for example, like the kind of transient inrush amps that you'd get with a non-variable speed motor. It's kind of continuous amps under its peak operating conditions.
Is it contingent on areas, zones, high usage areas, like zone 5 versus?
It would be running flat out. So
Doesn't matter.
if you had a multi-zone system, that peak would be based on, all zones calling for heat, maximum fan and compressor frequency, and so on. Okay, so that was the clipboard method, and that's what you're typically going to use. Once you have that data, you can gather that data in maybe 15, 20 minutes, run the spreadsheet in another 15, 20 minutes, and then you have a code complaint answer. Yeah, Jay?
And you mean the actual NEC, like Excel?
So this method is described in text in the NEC. I've built a little worksheet for this that's in an article that I'll link at the end. And you can then easily, create a spreadsheet with a little bit.
My cert actually created one because I took that one and so apparently the same thing. But they have one that they put together.
Okay, that's good to know. Yeah, that wasn't here a couple years ago when I was creating some of this stuff. So that's really good to know. So there's another method if you have access to that energy monitoring data. And if you have that data, it can be really quick. Essentially, what the code says is you should have maximum demand for a 1-year period. But then there's an exception. If you don't have a year of data, which you rarely will, as long as you have a full 30 days of data, you can take the peak 15-minute interval during that 30-day period. And that will tell you your starting peak watt draw. And then you have to add in a safety factor. It's a 25% safety factor. And I'll take you through this in a little more detail in the next slide. But once you have that data, you add in an extra 25%. And then you add in the additional loads that you're thinking about adding. And if that's still under the panel service rating, then you're good to go. So this is a screenshot from Emporia View. It's a home energy monitor that has little circuit transducers that you clip both into your mains for your panel, but also you can monitor individual circuits. And I'll look at some of that circuit monitoring data in the next couple slides. But on the home screen, it'll tell you what the monthly peak 15-minute demand is. So this is exactly the piece of information you need to do this calculation. So you can take that 8.45 kilowatts or 8,450 watts, convert it to amps. In this case, that translates into 35.2 amps. You need to add in the 25% safety factor. That brings you up to 44 amps. So the house, as is, has a peak of 44 amps. This was measured during a season when there was no heating or cooling going on, so it doesn't take that into account. But if we're removing the existing heating equipment and putting in a heat pump, we know from the submittal that, say, this heat pump has a rated load amps of 17, and we're also putting in a 5 kilowatt resistance heater. I convert that 5 kilowatts to amps. So with the existing demand plus the new demands, I can see here I am at 81 amps.
Comparing to your same house?
This was just an example because I had a screenshot for it, but I did do a,
Resistance heaters and the other ones in your
yeah, no, this was just an example. The next one is my house here. And so I have an older house. But I've insulated it very thoroughly, changed the windows, air sealed and insulated the attic, added some foam insulation under the siding, and then fully electrified it in 2020. With the last things I had to change were my heating system, so I replaced the gas furnace with a 1.5 ton ducted heat pump and a heat pump water heater. And I did these load calculations based on the house as is, or in its current electrified state. When I did the spreadsheet clipboard calculations, I got 74 amps. When I did it based on my measured data from the Emporia, it came in at 73 amps. I think it was, somewhat good fortune that these results came out so similar. My impression is that overall the clipboard method tends to be a little more conservative, and that the monitor data, because it actually sees how you're using the house, it can be a little bit, give you a little more room to work with the panel. But doing this circuit monitoring really led me to some, what I thought were some pretty fascinating results. So I ended up monitoring my house for 7 months. I had 22,000 15-minute intervals. And during the vast majority of these, 20,000 of those 22,000, I was using less than 2 kilowatts. This is a logarithmic scale, so you can see with each increase in power, the number drops. So even though I have to base my panel sizing on the peak, this was only 7 intervals out of 22,000. And so this gives you a sense that it's really these rare occasions that are driving the peak demand. I looked at these 7 intervals in a little more detail, and I found that in order to get those really high numbers in excess of 10 kilowatts on my panel, a couple different things had to happen. One was that my heat pump water heater needed to switch into resistance mode. So it was not keeping up. This happens in winter when I have colder incoming water temperatures. But then my dryer was also running during those periods. So my peaks were on laundry days. The heat pump was running, but it's only a small part of this peak. So, you know, I'm mainly throwing this in there to show you the kind of insights that you can get when you start monitoring your home energy. Yeah?
Do you know if NYSERDA is going to ever fund some type of monitoring like that?
I don't know. I mean, I think there's so much to be gained from it. In a few of my recent projects, I've thrown it in as a freebie just because I wanted those insights, but haven't had a chance to go back and actually analyze the data.
So, I mean, here, if your heat pump water heater is smart enough to know that the dryer was on, and decided not to turn on during those parts, you would have been probably get out of 60.
Exactly. And because I had plenty of room to spare, it wasn't an issue. But if I was bumping up against those limits, having that load switching would have been huge. And so I think actually in the next couple slides, I'm going to show a couple options for that. But yeah, I agree. Yeah.
Were you able to compare your monitoring measurements to your actual electric bill?
I did not do that extra step.
We're getting right now, you know, thanks about electric usage and a system like that, if it can actually calculate, you know, the actual usage versus the billed usage would be a
no, that's a great idea. I actually had to take my monitor out because I needed it elsewhere, but that would be good.
To see how close it is.
Yeah, no, I think it's a great idea. Yeah.
Were you saying you didn't have your heat pump water in heat pump mode, you had it in like a hybrid mode?
You know, that was one of the things I caught with this, was the fact that I should be using it, like we want to use these in efficiency mode, right? We don't want that resistance to kick on. It had somehow gotten back into hybrid mode, and so it was kicking on there.
Sorry, John. What size heat pump system do you have in your house, and what is it ductless or ducted?
I have a 1.5 ton ducted heat pump. I sized it really tight. I actually bought the electric heat kit, and it's sitting on top of the air handler, but I never wired it in because I didn't think I'd need it. It's a single zone. No. I decided, and I wouldn't do this in a customer's home until I'd done it in my home, but I did really tight sizing calculations, and I was able to get by with a 1.5 ton heat pump for the whole house.
I'm at, like, my house is similar parameters as yours, and I can't think about it too much. And I wonder though, is it for your system? Is it running like max all the time at the 1.5 ton, or are you finding that it's running on a lower output?
It's modulating the whole time. When we get below zero outside, which happens, you know, a few hours each year, it does slip a little bit. And I'm willing to accept that, honestly. I'd rather accept that, but that's not a choice I would make for a customer, you know. Just gonna do a quick time check. Okay, I'm gonna need to probably speed things up just a little bit here. Options for freeing up more space in the panel. So this isn't about amps, it's just about spaces. If we have unused branch circuits, for example, if we're replacing electric baseboard in a room with a ductless heat pump, we can use those spaces. We can install tandem and quad breakers, which I'll talk about in the next slide. We can install a sub panel. And there's times when we don't want to upgrade the whole service. We just need more spaces, so we can upgrade the panel and get more spaces that way. So tandem breakers are like what we see here. So in a standard sized space, we now have 2 single pole breakers. This is a very common strategy. To free up one space, you need to install a tandem breaker. To get enough for a double pole circuit, you're going to need 2 tandem breakers. Not all panels are going to accept tandem breakers, and some may set an upper limit on how many you can have. And there are also quad breakers, which are like basically double tandem breakers for double pole circuits. So in this case, we've got a tandem breaker here. The green handles go to the clothes dryer, electric clothes dryer, and the gray handles go to the stove. So that's another option. Because these have to clip into adjacent spaces to get that 240 volts, that's why it's organized this way instead of just 2 separate breakers. Sub panels are often a good option when you just need more spaces. Sometimes the sub panel can be right next to the main panel. It could be closer to the actual end use. So I've seen sub panels put out where 2 heat pumps are going to be installed, and that sub panel serves both those heat pumps. In some cases, you can put in a new 200 amp main panel, and then your old main panel becomes a sub panel of that. And then we're seeing some really creative strategies for cases where a service upgrade just is too expensive or prohibitively difficult. The underground service is one example. Improving the envelope, as we know, can help you downsize your heat pump. It can also reduce your need for supplemental heat. So we do this as part of the NYSERDA programs. We get homes heat pump ready. That reduces both the size and cost of the heat pump, but its electrical demands. And same thing by doing really good aggressive sizing calculations and taking in electrical power requirements into account during our HVAC design. If we can design without supplemental heat, we can save a big watt draw there. Installing lower powered appliances, whether it's refrigerators, dryers, etc., that can reduce your appliance loads. Circuit splitters, this is a plug-in example that I've shown here. Essentially, you plug your car charger and your dryer into this. And whenever you use the dryer, it stops charging the car. The rest of the time, the car charger is on. There are smart panels like the span panel that Hal mentioned that are another way to do this, where the entire panel is monitoring your loads, and you can designate circuits that will be shut down in case you start to get close to your capacity. There are also individual breakers that can do this. I believe Eden makes some breakers that will do that. If people are interested in digging into this, Redwood Energy has a tool called the Watt Diet Calculator that can take you through a lot of these different strategies. It's a really nice website. Okay, now heat pump water heaters. These are the other big thing that we're electrifying through home performance. These are highly efficient. So, a heat pump water heater installed in heat pump mode, not like I had it, is going to heat your water with, 3+ times the efficiency of a standard electric resistance tank. And when it's running in heat pump mode, it might only draw 400 or 500 watts. But the standard model still has the same 4,500 watt resistance elements. And so it's still going to require a 30 amp, 240 volt circuit, and it's going to count in your calculations as a 4,500 plus watt load. Most of the time that's fine. This design among heat pump water heaters is the one that's going to give you the best recovery rate. But if your capacities just don't work for that, there are 240 volt water heaters that have smaller resistance elements. You've now cut the size of the resistance element in half, and so that'll add less load to your panel. They typically have the same compressor as the 30 amp models. So if the house has lower hot water requirements, this may be an option. Now these are things that are relatively new in the market, and I'm really excited about these for a couple of reasons. The big thing being that repair-replace opportunity. People might have say a power vented natural gas water heater. It fails. They already have a dedicated circuit for that power vented water heater in place. They can use a plug-in heat pump water heater option. Now, these won't have the same recovery rate as the 240 volt models. So they're going to work better for smaller households. Some of these have a bigger compressor. They've gotten rid of the resistance elements, but they've got a slightly larger compressor, and so they may make a little more noise. But these are just an option to keep in your toolkit. There are also ones that can work on a shared circuit. So you have an atmospheric, non-powered gas water heater. It fails. You need to do an emergency replacement. You can now use a 120 volt water heater that can plug into a shared basement circuit and becomes essentially a drop-in replacement. Now, these are going to have lower recovery rates, lower first hour ratings, and so they're going to work best for small households with lower use. It's important to do the calculations to make sure you're putting in the right water heater for the household that you're working with. Cooking, the last things I'm mentioning here are other things that we need to electrify in order to shut off the gas meter. People tend to be really attached to their gas stoves. Once you've used an induction cooktop, if you haven't used one, you'll just be blown away by the level of control. I'm a person that's always burning whatever I cook. And the level of control I get with induction cooktop is much better than even a gas stove. I just have a plug-in countertop unit here, but there are also full-sized ranges. These are going to have electric draws comparable to electric resistance range. They're going to use 40 or 50 amp circuits. So they are going to be a big electric draw in your worksheets. Clothes dryers, this is sometimes the last thing that we need to electrify so that we can shut off the gas meter. Our standard electric dryer is going to take a 30 amp breaker and draw about 5,000 watts. There are also condensation dryers and heat pump dryers that have much lower wattage requirements. Another advantage of these is that they don't require a vent. So in cases where, say it's an interior of a apartment, for example, these don't require a vent. They can just drain the water into a plumbing drain. The disadvantage is that they're more expensive to buy and they're a lot slower. So they're definitely not for everybody. And clothes drying is rarely a big part of someone's overall energy bill. So where the panel and the house will support it, probably this is what most people are going to end up choosing. We're starting to see more and more electric vehicle chargers. You know, as Courtney mentioned, probably a quarter of people are planning to switch to electric vehicle on their next purchase. And they now represent about 10% of all vehicle purchases in the US. The most economical way to charge your vehicle is not at a charging station. It's at your own home where you can pay your standard residential rate. So as far as us as energy advisors and people talking to customers, the thing to know is that there are 3 levels of chargers. Level 1 is just a plug-in charger, plugs into a shared circuit, 120 volt in the home. It's very slow, but if you're just doing a little bit of driving, or it's something you can throw in your trunk and take along when you're visiting family or something like that and keep your car charged that way. Level 2 chargers require dedicated circuits. They're 240 volt. The more amps you set these up with, the faster your vehicle is going to charge. So especially if you're driving a larger vehicle, a pickup, for example, you're going to want a larger level 2 charger. These can add significant draws to the home. They're also considered continuous loads, so they need to be counted at 100%. You don't get to derate them the way that you do appliances. Now, these are a great candidate for those load switching breakers and other load switching devices, because if you have to interrupt your charging for an hour to dry a load of clothes, no problem. So that's often a great way. And those split volt devices that I showed in an earlier slide are remarkably affordable. So let's see. Yeah, I'm gonna skip a few slides here. These are the critical pieces of the heat pump submittal when it comes to the actual installation. The MCA, the minimum circuit ampacity, tells you the ampacity of the conductor you need to use. And the MOP tells you the breaker size. And so if you're doing QA on one of your installs, these are things that you can check. There are different types of connectors, conductors. It's good to become familiar with those. A couple things to keep in mind. One is that wire gauge and ampacity are absolutely critical in delivering power to these. When we look at control applications and communication applications, a lot of manufacturers are going to want to see stranded wires because they're better at transmitting the communication signals compared to solid wires. And they'll often specify a specific wire type and gauge. For example, the mini splits I'm familiar with, it needs to be 14-4 mini split communication wire, and it needs to be stranded, not solid. We need to have a means of disconnect at every unit. This can either be a standard disconnect like the one shown here, or a outdoor sub-panel or panel, but it needs to be within line of sight. The heat kits on air handlers are powered separately, and so we'll need a disconnect there. Same thing with heat pump water heaters. If they're not in direct line of sight of the electric panel, you will need a disconnect on those. These handle locks can serve as a alternative in cases where there's not been a disconnect installed. This allows you to lock out that breaker while you're working on it if it's not within line of sight. There needs to be a convenience outlet within 25 feet. This is for the technician working on the heat pump to plug in their tools. If there's already an existing GFCI outlet within 25 feet, you're good to go. If not, you're going to need to install one, and it's going to need to be on its own breaker. It can't pull power from the 240 volt circuit. Penetrations need to be sealed. This is just basic weatherization, but we have had inspectors flag us for this if they didn't like the way that we did it. But it's really critical to stop infiltration, water entry, and insects and spiders from coming in. And it needs to be something that's outdoor rated, either a UV resistant foam, a duct seal material, outdoor rated silicone caulk. Power quality is really important for heat pumps. They have a lot of sophisticated electronics. So at a minimum, every heat pump should have a surge protector. In areas where you've got brownouts, you may also want to include brownout protection that shuts the system down if the voltage falls below recommended levels. If you've got persistent high or low voltage, you may need a buck boost transformer that can either bump up the voltage or down to bring it within the manufacturer's recommended range. And thankfully, the codes don't require us to put GFCI on our heat pump equipment right now, but that is likely going to be coming sometime in 2026. I suspect that we're going to see a lot of nuisance calls from systems that have been shut down on ground fault. So just something to be aware of. So if you want to learn more about the calculations I described here, these are a couple articles in Green Building Advisor. And I also have another one on reading heat pump electrical requirements. And there'll be an article coming out in Fine Home Building in the April edition that goes through the different options with 120 volt as well as 240 volt water heaters. Just because I think those are going to be something that we're going to see more and more as we look at this emergency repair replace. Yeah, Jay.
On the water heater, so the typical hybrid has three sizes, 50, 65, 80. We try to match that based on the household size and their habits, but sometimes we miss.
Yeah.
End up with a 50 and they start complaining about running out of water.
Yeah.
And it's hard, it's a very expensive to upgrade it at that point.
Oh, sure.
So any suggestions of ways you can get a few more gallons out of one of those if you didn't quite size it right?
Raise the water temperature at a mixing valve.
Yeah, that's standard.
That's pretty much it. There are crazier things you can do. You can add a tempering tank on the incoming water, but I think bumping up the set point and adding a mixing valve is the go-to solution. And what it means is the heat pump's going to operate less efficiently because it's trying to heat hotter water, but it may be an acceptable sacrifice. I think, like you said, a lot of it comes down to really trying to understand the needs of the house, not just in the present, but you've got a couple kids that are about to enter their teens. Well, maybe that's a time that you want to go ahead and get that 66 or 80 gallon water heater. And then the other thing that I've learned to always ask about is the jacuzzi tubs, because those large draws on those tubs are what really deplete the hot water.